So dark matter, why is it dark and does it matter? And for a long time now we've known that the universe has a dark side, and it means that there's a lot of the universe that we can't actually see or at the moment perceive in any real way. So like this lecturer would say, it's getting a bit confusing because we've discovered antimatter and we've discovered dark matter, and we've just confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. And that's, I think, the state of confusion and misunderstanding amongst a number of people when you start talking about antimatter, which has been around for a while, dark matter, which is an apparently more recent thing. You start to wonder, well, if it's really out there, how come we haven't noticed yet up till now? The bottom line is that if we look at the composition of matter and we divide all matter into stuff we know about and stuff we don't, it's embarrassing to say that the stuff we know about is only about 16% of all the matter that exists. Something of order 84%, the numbers might change a little bit year on year as our understanding improves, but something like 84% of matter is matter that we can't actually see. If we look at the 16% that we think we do understand, how is that subdivided? Well, most of it isn't stars, as you might think, but actually most of that ordinary matter is actually just gas, hydrogen and helium floating around the universe. Only a very small amount, the little yellow wedge there, is made up of stars, and there's also a few other particles floating around, mainly neutrinos, very lightweight particles, that are floating around the universe as well. So when you look out on the night sky and you see stars and galaxies which are made of stars, you might think that most of the universe seems to be made up of stars and a bit of other stuff. But actually it's the other way round. The universe seems to be made of some stars and a lot of gas and a huge amount of something else. So I'm going to be talking in this talk about what dark matter is, or at least how we've come to understand dark matter. Why is it dark? What do we mean by dark matter? What's the evidence that makes us think dark matter exists? There's a number of independent strands, and 4 of them are covered in the handout. I think in this talk I'll be covering the first 3 of those strands of evidence. And then we'll ask the question, well, what actually is it? After we've gone through the evidence that something exists that we call dark matter, we'll then ask the question, what is it? And then we'll wrap up with, well, does it actually make any difference to how the universe works? So firstly, why is it dark? Well, the simple answer is because it's not light, but that's a rather fatuous answer. Let's be a little more useful. Dark matter does not behave the same way as ordinary matter, in the sense that ordinary matter interacts through what we call the electromagnetic force. That means it emits and absorbs electromagnetic waves, in other words, light. And here I'm using the word light not to mean visible light, but to mean any light, whether it's infrared, visible, ultraviolet, X-rays, gamma rays, radio waves, anything that is electromagnetic. Ordinary matter will generally emit and absorb electromagnetic light, waves, i.e. light. And hence ordinary matter can be detected through its interaction with light, whether it be absorbing or emitting. Dark matter does none of these things. That's why it's in a category all by itself. So if we think of ordinary matter, you, me, the cat, the dog, the trees, everything that's out there is made of atoms. And atoms we can think of, not strictly accurate, but good enough, we can think of an atom as being this sort of picture here. A little ball of positively charged matter, which we call the nucleus, and that's surrounded by a buzzing set of electrons that are negatively charged. And it's the way these positive and negative electrical charges behave that determines the way matter interacts with light. The electrons go bouncing around between different energy levels when they absorb or emit light. And we understand that pretty well. For the last 100 or more years, we've got a fairly good understanding of what atoms are and how they work. But what's the evidence that there's something beyond just ordinary atoms in the universe? Let's look at the first piece of evidence. Evidence piece number 1, galaxies in clusters. So what is it that holds galaxies together in clusters? If we have a look at a a cluster here. We have lots of individual galaxies, maybe hundreds, maybe thousands, maybe more galaxies, all appear to exist in a cluster. What's holding them all together? Well, no, it's not a trick question. It's gravity that's holding them all together. If gravity wasn't strong enough to keep them all together, we would expect them to drift apart, and we wouldn't see so many clusters all over the universe. Gravity depends on mass. Perhaps that's no surprise to anybody. How can we get an idea of what is the mass of this galaxy cluster, or indeed any of the individual galaxies within the cluster? Well, we can actually get a fairly good estimate without going anywhere near the galaxy to weigh it. We can get a fairly good estimate just by looking at how luminous it is, how much light is coming from the galaxy. If we measure the galaxy brightness, and assuming we understand stars, and I think we do have a fairly good understanding of how stars work, so if we know the brightness of the galaxy, then we can estimate how many stars there must be in that galaxy to produce a given brightness. And if we know how many stars are there, then we know, roughly speaking, the mass of all the stars, and hence we know the mass of the galaxy. That's predicated on the fact that we do have a reasonably good understanding of how stars work, how they're born, how they live, how they die, what their masses are, what their brightnesses are. And if we want to throw that away and say, well, maybe we've got the mass of the galaxy wrong because we don't understand how stars work, well, that means we have to throw away pretty much everything we understand about astronomy and astrophysics and stellar evolution, galactic evolution, the universe evolution. The way stars work is based on our understanding of nuclear physics, and that is fairly solid ground. So although we don't know the mass of the galaxy accurately to the 6th decimal place, we do have a pretty good idea of the mass of the galaxy based on the number of stars that it contains. And if we can do that for one galaxy, we can do it for all the galaxies, and hence we get the total mass of all the galaxies in the cluster. Now we have an estimate of the mass of the cluster, and hence we have an estimate of the amount of gravity that should be keeping all of those galaxies together in that cluster. But ever since the 1930s, perhaps a little further back than you appreciate, it's been a problem now for almost a century. As early as the 1930s, it was realized that the gravity that we calculate by looking at how luminous a galaxy cluster is, that mass is not enough to keep the cluster together. The galaxy should have drifted apart long ago, and we shouldn't see so many galaxy clusters dotted all over the universe. So there's a problem with the amount of mass that we can calculate. So this is an old problem. Dark matter sounds fairly recent, but actually it's a century-old problem. Using the luminosity to find the mass seems to underestimate the mass, not by a few percent, not by 10%, not by 50%, but by huge orders. It could be a factor of 2, a factor of 3, a factor of 5, a factor of 10. It's a huge discrepancy. And here's a phrase that I'll use more than once. It would seem, it's as if there's some additional mass that is not luminous, it doesn't show up when we count stars, that's providing the extra gravity needed to keep the cluster intact and bind the galaxies together. And we don't know what that is. Let's call it dark matter, because that sounds pretty cool. In the original discussions, it was simply called the missing mass problem, but these days we simply give it the label dark matter. Let's think of a second strand of evidence, which technically speaking is completely independent of the first, but goes along similar lines. Let's have a look not at galaxies in clusters, let's have a look at stars in galaxies. All galaxies rotate to some degree or another, and we can ask how fast are the stars moving. We can use the Doppler effect, perhaps you've heard of this. We can look at the spectrum from stars that might be unshifted relative to a laboratory source that we can test, or they might be shifted towards the red or the blue end of the spectrum. And that will depend on how the stars are moving. So in this little cartoon of a galaxy rotating, if the stars are moving towards us, then the light from those stars will be blue shifted. Whereas if the stars are rotating such that they are moving away from us, then those stars will show spectra that are shifted towards the red end of the spectrum. Any stars that are moving across our line of sight will not appear shifted. So this is a very rough schematic of what's being shown on the left, where we would look at the full spectrum and we would look at where the absorption lines are that are characteristic of particular elements, and we would compare those to laboratory sources to tell us whether the star is moving towards us or away from us. So we can do that with essentially any galaxy which is close enough to see stars and measure their spectra. So we wouldn't use a galaxy like this. This you perhaps recognise is M51, the Whirlpool galaxy. Here all the stars are moving, roughly speaking, in the same plane, which is perpendicular to our line of sight, and hence very few of the stars are actually moving towards us or away from us. So we wouldn't use a galaxy like that. Here, quite a few stars are moving towards us or away from us because we're looking at a spiral galaxy edge on. However, you can see from the line down the middle of the galaxy, there's a lot of dust obscuring the light from the stars, and that will get in the way of us measuring their spectra accurately, and so we wouldn't look at a galaxy that is purely edge on either. We would look at something that's in between face on and edge on. Let me just hide the video panel again and whoops, hide the floating meetings control. There we go. So we wouldn't go for face on, we wouldn't go for edge on. We would do something that we would look at a galaxy that's a little bit between the two. So here, for instance, this is not supposed to indicate the star's true colour, it's just a colour coding to show what we would expect. If the stars at the upper region of the galaxy are moving towards us, we would expect them to be blue shifted. If the stars on the bottom here are moving away from us, we would expect them to be red shifted. And stars in this middle region would neither be red nor blue shifted. So what do we actually find? What do we expect to see for the orbital velocity? What would we expect to see for how fast the stars are moving as a function of where they are in the galaxy? How should it vary as we go from the middle of the galaxy towards the edge of the galaxy? If all the mass that's keeping the stars in orbit around the galaxy is inside the orbit of that star, we would expect them to behave like planets in the solar system, where most of the gravity is produced by the sun. And so regardless of whether you're talking about Mercury, Venus, Earth, Mars, or the outer planets, Uranus, Neptune, for instance, they would all be pulled towards the centre of the solar system by the sun. The planets have very little influence on each other. We could plot this slightly differently if we wanted to. Instead of plotting the speed as a function of position, we can plot it using a log scale if we so wish, which shows us the relationship a little more clearly. But for this purpose, I'm just going to show the speed as the vertical axis and how far we are from the centre of the system as the horizontal axis. The important thing is that we would expect that as we get further and further away from the centre of the system, the orbital speed will get lower and lower. So for instance, Neptune out here is moving very slowly compared to the other planets, simply because it is such a long way away from the main source of gravity that's holding it in its orbit. So when we look at a galaxy, do we see anything like the same thing? So here again, we're looking at velocity vertically as a function of how far we are from the centre of the galaxy, and I've plonked a little picture of a galaxy in the background just to give us a little bit of context here. So when we're quite close to the centre of the galaxy, as we move out, what we actually find is that the speed at which stars are moving is going up simply because more and more mass is within the orbit of the star. What's important is what happens once we've gone beyond the reaches of what we would consider to be the visible part of the galaxy. So once we've gone outside this sort of region, the red ellipse contains, I don't know, perhaps 99% of the mass of the galaxy is within that red ellipse. What happens if we look at stars any further away? Because now essentially all of the gravity of that galaxy appears to be coming from within the red ellipse there, what we would expect is that any stars that are further away from the galaxy, we would expect their velocity to decrease just like we saw for the planets in the solar system. So what do we actually see? Well, unfortunately, it's a bit tricky to find stars out here. Most of the dots you can see in this picture are in our own galaxy. They're not stars that belong to this galaxy. So if we want to find out how fast would things move if they were orbiting out here, we don't find enough stars to make that useful. But luckily there's lots of hydrogen out there. Let me just see what's being asked here. Are we being asked? It looks like somebody else is knocking to come in. Let me invite them in. Is that somebody else that's... There is somebody waiting in the room. I will let them in. Okay, we now have another participant. Excellent. Right, so I was saying that we can't use stars outside this red ellipse, but we can find a lot of hydrogen gas out there, and we can take the spectra and work out what this hydrogen gas is doing. And the question is, will we find that it comes back down, which is what we would expect based on the visible light from this galaxy. What we actually find is, no, the velocity doesn't come down as we go further and further away from the galaxy. In some cases, the velocity flattens off. In some cases, like this, it actually goes up. And the gas is moving more and more quickly as we go further away from the galaxy. Which doesn't make sense if most of the mass of the galaxy is contained where we can see the visible glow from the stars. So again, there seems to be something that is providing additional gravity to keep these stars, and in particular this gas, moving at the speed that it is. So here's the phrase once again. It's as if there is some additional mass that is not luminous, because we can't see anything beyond the edges of the visible edge of the galaxy. Something is providing the extra gravity that is needed to keep the stars, or in this case the gas, orbiting at high velocities, even a long way outside the visible edge of the galaxy. Not just outside the visible edge by 10%, not just by a factor of 2, in some cases by a factor of 5, a factor of 10 further away than what we would perceive as the edge of the galaxy. Something appears to be providing additional gravity. It looks like dark matter again. So one way of visualizing this is to think, what would the rotation of a galaxy look like without dark matter? What we would expect is that the stars would be moving very rapidly close to the center of the galaxy, and they would be moving very slowly out here on the edge, a long way from the edge of the galaxy, a long way from the center of the galaxy. Right at the edge, we would expect the stars to be moving very slowly. Whereas what we actually find is that the stars at the edge, if you look at the similar place here, if you look at what's going on here, for instance, we find stars moving much more rapidly than what we would expect if there were no dark matter present. So left is what we would see without dark matter, right is what we actually see when we observe spiral galaxies, and hence we deduce the existence of additional dark matter. That's the second piece of evidence that there is missing mass in the universe. Now I'll say something about a third strand of evidence. So this one is quite unlike the previous two. The previous two were very similar. What's the gravity that keeps galaxies together in a cluster, and what's the gravity that keeps stars together in a galaxy? This one is different. We can calculate mass from its gravitational effect. Not on galaxies in a cluster or stars in a galaxy, but we can calculate mass from the gravitational effect on light itself. Now, yes, we know that dark matter does not interact with light. Yes, we've already agreed dark matter does not emit or absorb light. That is true. But if dark matter has mass, then it has gravity, and gravity can bend light. So in principle, we can detect the existence or infer the existence of dark matter from its effect of bending light. So let's have a look at how that might work. In this particular diagram, we have a very distant galaxy on the right-hand side. There it is, and it's blown up just so you can see it a little more clearly. And the light from that galaxy travels to Earth, where we detect it in a telescope of some kind. But if in between the distant galaxy and Earth there's a large galaxy cluster, for instance, producing a very large amount of mass, then that mass can make the light bend, because mass can bend light. One way of thinking of that is to think of mass distorting space. In the background we have this grid structure, and you can imagine that if this was the structure of space, the existence of mass can bend or warp space, and that can in turn make the light bend. So it doesn't really matter how you think of it. All that matters is that mass has gravity, and gravity can bend light. So we have a very large cluster of galaxies here, and occasionally, whenever we see a cluster of galaxies, we might see something behind that cluster that has been lensed by the light from that distant galaxy getting distorted as it moves through the galaxy cluster. So for instance, the galaxy might be so far away that it looks like just a little bit of a dot, but when we actually observe it through this very mangled looking lens, we might see a rather distorted view of that lensed galaxy. So here's one example, for instance. This orange blob in the foreground is actually a galaxy that is, relatively speaking, quite close to us. And in the distance, which we can't really see too well, is a bluish galaxy. But what we see of that galaxy is this very distorted image of the galaxy. The galaxy itself is not the shape of a horseshoe. The horseshoe is just the result of the light passing by this galaxy or collection of galaxies and being distorted by the gravitational lensing of that galaxy or cluster of galaxies. And if you find it difficult to see how it is that a distant light source like a galaxy could possibly be distorted into an arc or a horseshoe, then there's a very interesting analogy that helps you get your head around what's going on. For instance, if we look at this light source, a candle, and in between the candle and us taking the picture, if we insert a lens, such as, for instance, the base of a wine glass, we can see that that candle doesn't any longer appear as a single light source. It now appears as multiple little arcs. You can imagine that it would be a complete circle if all of those arcs joined up. In this particular case, it seems to be the candle has been distorted into two candles, one on one side and one on the other. It depends on precisely where the light source is relative to the lens. And in this particular case, if you hold the lens in just the right position, it is possible that the candle is imaged as a complete ring of light, just a little bit like the horseshoe that we saw just a moment ago. So depending on how the glass is arranged and how thick the glass is, we can distort the light from the distant light source such that it produces a distorted version of the candle, or it can produce arcs, or it might even produce an entire circle of light. And that's what happens when we look out into the universe. We see clusters of galaxies such as these yellowy orange objects here, and in the great distance we can see distorted views of other galaxies. Here we see a very elongated stretch here, which appears to be a distant galaxy stretched into a line, when we can see other arcs that are coming around the whole cluster of galaxies. We can see various blue lines and distorted galaxies in the background. The distorted images, the amount of the distortion, can effectively tell us how much mass is in the lens. It's actually relatively easy to do the calculation of, assuming we have this much mass, how would we expect the light to bend around that mass? In other words, given an amount of mass, how does that mass distort space, according to Einstein's theory of general relativity, and hence, how does it bend light? That might not sound easy, but that's a relatively easy calculation to do. What is quite tricky is to say, if this is the amount of distortion that we actually see, what mass must have produced that distortion? So we can easily start with a simple mass and say, how does that distort light? It's a rather tricky calculation to take an image such as the one I've previously shown, with lots of distorted galaxies all over the image, and then ask the question, well, what must the distribution of mass have been, and how much mass must there be in the cluster in order to produce that much distortion? When the calculation is done, tricky calculation, but it's possible to do it, we find that the amount of light required to distort the distant galaxy, the amount of mass required to distort the distant galaxy is more than the mass we can see in the lens of the galaxy cluster. Once again, it's as if there is some additional mass that is not luminous, it's not showing up by counting stars in the galaxy, that's providing the extra gravity that's needed to bend the light and produce the distorted images. Dark matter once again. The fourth strand of evidence I'm not going to talk about. It's related to the cosmic microwave background. It's covered in the handout that I'll refer you to later. It's covered in the handout, but I'm not going to cover it in the talk here. Okay, we've had three strands of evidence that says there's far more mass out there than we can account for by looking at the luminous mass. The mass that produces and interacts with light is not enough to account for all of the mass that we think is there. So there's a lot of evidence, but what actually is it? Well, there are two main candidates for the composition of dark matter. Hereafter I'll just abbreviate that to DM. There are machos and there are WIMPs. Machos, massive astrophysical compact halo objects. I think that acronym was constructed so as to produce the acronym MACHO because it sounds really good compared to WIMP, weakly interacting massive particles. So let's have a look at each of those as candidates for what dark matter actually is. Firstly, machos, massive astrophysical compact halo object. Massive, well, it has to have mass. Whatever these things are, they have to have mass to produce the gravity. Astrophysical means nothing in particular. Compact means they are physically quite small. And a halo object is an object that exists in the halo of a galaxy. So here we see, does that mean somebody else wants to come in? I don't see another person waiting, so okay. So the halo of a galaxy, we can see here what appears to be the edge of the dust region of a galaxy, and there's this perfusive glow around the rest of the galaxy because there is a certain amount of gas and dust that exists beyond the easily visible edge of a galaxy, and the halo is the general spherical region. Even if the galaxy itself is a disk, there usually is a spherical region around the galaxy that contains a certain amount of a few stars and gas as well. But it would appear that dark matter extends much further than this visible halo. The visible halo might be a certain size, but the dark matter halo, the region of space that appears to contain dark matter, could be up to 10 times larger than that. But we do know that there are objects like globular clusters, etc., that exist in the halo of galaxies. So is it possible the halo contains other objects, such as machos, that could explain dark matter? Might there be bodies that are made of normal matter that emit no light? For instance, black holes, neutron stars, white dwarf stars. You might find it odd that white dwarf stars are in the list of objects that emit no light because clearly white dwarf stars are white. But they're only white for as long as they're hot, and eventually they're going to cool down, and eventually a white dwarf star, despite its name, will no longer be visible because it will simply cool off to the point where it no longer emits any light. I'm still getting some indication here that somebody is waiting. Okay, I will admit Edmund again. Okay. Right, where were we? White dwarf stars at the end of their life will appear white, but as they cool down, they will eventually no longer be white. They will simply fade away and eventually will be dark objects. So they will absorb light, but they won't emit much light. So is it possible that these objects, black holes, neutron stars, white dwarf stars, might be dark matter candidates, these black bodies? How could they be detected? If we're looking for light, we're not going to get very far. If we're looking for black holes, neutron stars, etc. Yes, we can see black holes from the amount of light they emit around their event horizon, so some black holes are visible, that some black holes might be difficult to detect. But we should be able to see these objects by gravitational microlensing. Let me explain what microlensing is. It's the same sort of lensing that we saw with large objects, but simply on a much smaller scale. So the left-hand panel says that if we're looking at a distant star, we might see that star with a particular brightness. But if, as in the middle panel, a black hole or some other object happens to sit in between Earth and that distant star, it just happens to be wandering by and happens to end up in the line of sight between us and that distant star, then that black hole can bend the light, can lens the light, and the star for a very short period of time will appear a lot brighter and then go back and fade again as the black hole, or whatever it is, moves away. So just like lensing, but on a much different time scale, because the black holes or neutron stars or white dwarfs are assumed to be going around the galaxy like everything else, they will sooner or later happen to drift in front of a star. So if we look at enough stars and keep looking at them, we might see stars brightening as objects go in front of them. So that was a project that started a few years ago. This is an indication of what our galaxy looks like. So there's the main disk of the galaxy down the middle, and in the bottom right hand side we can see a couple of little smudges there. Those are the Large and Small Magellanic Clouds, which are within the halo of the Milky Way. So if we are in the main body of the Milky Way and we look at the stars that are in the Large and Small Magellanic Clouds, we would expect a few of these machos, a few of these objects, to drift in front of the stars that we were looking at in the Magellanic Clouds, and we would expect those stars to brighten every once in a while as one of these machos drifted in front. So that project was carried out. Basically thousands, or I'm not sure how many, maybe hundreds of thousands of stars were monitored to see how often an object moved in front, to see how often we got an increase of light due to this micro-lensing. And indeed, lots of objects were found. And it was calculated that if we find this many objects between us and the Magellanic Clouds, then if we scale up, there must be a certain number of those machos within the entire Milky Way. And there were billions of such objects. However, when it was calculated what they would contribute to the mass of the Milky Way, it was found that they would account for, at best, only a few % of what we need for dark matter. In other words, all of the black holes, neutron stars, white dwarfs that appear to be invisible but still within the Milky Way aren't anywhere near enough to account for the dark matter. The dark matter of the Milky Way is substantially more than the visible mass of the Milky Way, and these machos only account for a tiny fraction of what we need. So machos do not appear to be the answer. What about WIMPs? What about weakly interacting massive particles? So they're massive particles, they are part of the particle zoo. We know what atoms are made of, neutrons and protons and electrons, and we know of lots of other particles that exist because we've been smashing atoms together for a long time now. But maybe there's some particle that we've missed. It has to be a massive particle in order to account for dark matter. And by weakly interacting, that means that it shouldn't be interacting with light. It shouldn't be absorbing light or emitting light. It should be interacting with other particles via other forces, including gravity, but not including the electromagnetic force. So that's what's meant by a weakly interacting massive particle. Gravity, but not electromagnetism. So neutrinos are one of those particles. We don't have to worry about exactly what a neutrino is. A neutrino is a particle that fits that bill, except that it's not massive enough. Neutrinos indeed do not interact with the electromagnetic force, but they are too light. We need something that's like a neutrino, but much heavier and probably not moving so fast. Whatever these WIMPs are, if they exist, they were presumably born in the Big Bang. Separate talk entirely, the beginning of everything. So everything appears to have been born in the Big Bang. As far as we know, nothing has come into existence since the Big Bang. So they came into existence in the Big Bang, and every particle seems to have an antiparticle. That's our understanding of how the universe works. So if dark matter particles exist, then there must be dark matter antiparticles as well. annihilation between the two, as any particle will annihilate with its antiparticle equivalent, that seems not to be happening as far as we can tell, although we haven't made a huge effort to go looking for that. So there might have been a lot of annihilation of dark matter and anti-dark matter particles in the early universe, but it doesn't seem to be happening much now. If they are still around, and we would expect the concentration of dark matter particles, well, where would we expect them to be? We're not too sure where the dark matter particles are, if they exist, but would they not be attracted to other mass by gravity? So wouldn't we expect them to be in the centre of the sun, along with all of the particles we do understand? Simply because the sun has got a very large mass, wouldn't the dark matter be attracted to the mass of the sun? So maybe there are lots of WIMPs in the sun, and if they annihilate with each other, maybe they could make particles that we could detect. So that's the assumption. It's worth looking to see if we see any sign of dark matter particles in the sun. So we expect them perhaps to make neutrinos. We don't know, but that's one of the models. And if they do make neutrinos, then we have to ask ourselves, how are we going to detect these neutrinos? Well, we've been building detectors to detect neutrinos for a while now. One of them is this very big water tank sitting in Japan. It goes under the wonderful name of Super Kamiokande. So here we have a very large tank of water. Why would a large tank of water allow us to detect very energetic particles coming from the sun? Well, we can use an analogy of what happens when we take an object like a fighter jet and fly it through the air faster than sound. If we have a supersonic aircraft, what happens is it generates shock waves, and you're familiar with the idea of a sonic boom. If a particle travels faster than sound can travel through the air, then we get a sonic shock wave, a sonic boom. And light has an equivalent to that, and it goes under the name of Cherenkov radiation. So just like we get a sonic boom if a plane flies too fast, if we look, for instance, at a nuclear reactor, it glows this wonderful blue. That's nothing to do with Hollywood adding a little bit of an extra gel to make it look cool. This is what actually happens if particles, in this case energetic particles from the nuclear reactor, travel through the water faster than light. And by that I mean travel through the water faster than light can travel through the water. This is not the same speed as light travelling through a vacuum. If particles can travel faster than light can travel, then we get the analogue of a sonic boom. In this case, it's a flash of blue light. So what that means is that if we've got our water tank and we have a very energetic particle come, for instance, from the sun, and it passes through the water and travels through the water faster than light can travel through the water, we get a flash, and that light tends to travel in the same direction as the particle was traveling, and this blue flash is called Cherenkov radiation. So if we have this large water tank and we have light detectors along the walls of the tank, we would see that on the right hand side we would detect light because of this flash, and on the left hand side we would not detect that light because the light would be travelling in the direction that the particle was travelling in. So to give you an idea of what this looks like in its true size, this is the inside of the tank when it's been emptied of water, and if you're having trouble seeing what that central object is, that's two men in a dinghy. So you can get an impression of just how large this water tank is, and obviously at some point it would be filled with water, and each of these little footballs that you can see there embedded into the walls and the floor and the ceiling are the light detectors that would detect the blue flash, and in combination they would tell us from which direction this particular energetic particle had arrived. And then of course we can work out whether or not that's the same direction as the sun or not on any given day of the year. These are the light detectors themselves, these little footballs that contain photocells and the electronics required to detect the flash of light. We don't have to use water tanks, that's one experiment that's going on, but there are alternatives. These so-called photomultiplier systems are also embedded not only in a water tank, but there's a similar system working at the South Pole. It's called IceCube, and there's a laboratory there, but that's on the ice cap. That's not where the action is. The action is all below the ice cap, embedded in the ice itself. Those photodetectors are actually arranged on a sort of string of pearls, which then goes down on all of these lines from the ice cap down to the bedrock 2.5 kilometers below. Just to give you an idea of scale, if you're struggling there, on the right hand side, that's how big the Eiffel Tower would be to scale. So effectively, instead of having the particles travel through water and looking for a blue flash, the particles are travelling through solid water, i.e. ice. The advantage is the ice is already there, it's very pure, and it's uncontaminated from anything that's going on at the surface. So all you do is make sure that you bury all of these light detectors as deep as possible in a chunk of ice that's approximately 1 kilometre by 1 kilometre and about 1 kilometre off the bedrock there, something like 1.5 kilometres below the ice cap. So this particular cube of ice is 1 kilometre on a side. That's why it's called the ice cube experiment. So we can use water, we can use ice, but there's one other medium that we could use to see if these particles exist. It's a slightly different angle. We can ask ourselves, as well as having possibly dark matter particles located in the sun that might produce some very energetic particles, it's also possible that a lot of them are centered in the Milky Way. The Milky Way has a large black hole, 4 million solar masses. Perhaps there's a lot of dark matter concentrated around there as well. And it's thought that dark matter in the center of our Milky Way galaxy could produce some very energetic gamma rays. And there are experiments planned to search for these. And again, we're moving away from using water and using ice. There's a different way we can detect the very energetic particles that might come from the center of our galaxy. Again, this is a picture of our Milky Way with the center of the galaxy in the middle, because that's the way it's been presented. But in terms of where it is in our skies, from England, the centre of the Milky Way galaxy is quite a long way towards our southern horizon. So if you wanted to build an experiment to see if anything is coming from the centre of the Milky Way, you wouldn't build it in England, you'd build it somewhere in the southern hemisphere. So there are now plans to build the so-called Cherenkov telescope array, a collection of telescopes, for instance in the Atacama Desert, such that you look up at the sky and you look for blue flashes in the sky. In effect, instead of a water tank or an ice cube, you're now using the entire Earth's atmosphere as the detector. And if very energetic particles are travelling through the air faster than light, again, particles travelling through the air faster than light can travel through the air, then it will produce a characteristic blue flash. And these telescopes would be looking for this characteristic blue flash in the sky, and by using lots of telescopes over a large land area, you'll be able to figure out where these particles are coming from. As indicated in this little artist's impression here, a very energetic gamma ray or particle coming in would tend to produce a shower of particles, which would then produce this blue light that would then be caught by quite a number of these telescopes. There are other attempts to detect dark matter. There are these large experiments, water tank, ice cubes, Cherenkov telescope arrays. But in principle, you can think about ways of detecting dark matter on smaller scales. So there are a number of different experiments in progress. I'm not going to go through the detail of how they work, but if you wish, you can go away and look up what these various experiments are. They're being carried out. A lot of them are in Europe, some of them are in the States or in Canada. And each of them is taking a slightly different approach as to how the dark matter particles might be detected if they exist. Many of these experiments have been running for a few years, and they've observed something. They've observed some little blips that could be the detection of dark matter particles, but many of the detections have either been ruled out as spurious, or they're contradictory, or they are simply waiting confirmation. So there are some interesting possibilities, but no one has yet definitively said, yes, we've seen a dark matter particle in our experiments. And yes, there are alternatives. There is another possibility. We know that by looking at all the mass we see, the gravity doesn't seem to work. If we add up all the mass of what's in a galaxy cluster or what's in a galaxy, that doesn't seem to provide the gravity we need to explain the observations, and hence we say it looks like we need additional mass. But the alternative is maybe we don't know how gravity works. Maybe we've got gravity wrong. That's a big statement. But maybe we only seem to need dark matter because the matter that we've already got is enough, but we're not accounting for its gravity correctly. Maybe gravity, which we think of as being universal, maybe it works differently on the scale of the universe or the galaxy or the solar system. In other words, we understand gravity well enough to figure out that apples fall to the surface of the Earth and the moon stays in orbit around the Earth, and we understand gravity well enough to get a probe out to Pluto. But maybe when we think about larger scales, maybe gravity doesn't work the same way when we think about the galaxy compared to when we think about the solar system. And again, when we think about the universe in general, maybe gravity works differently. Maybe we have to modify gravity depending on the scale that we're dealing with. Maybe gravity is not universal. So there's a theory called modified Newtonian dynamics, MOND, whereby in effect you apply what some people might call a fudge factor. You apply a modification to Newtonian dynamics to account for the fact that it works like this on Earth, but it works like that in a galaxy, and it works like that in a galaxy cluster. You take all the observations and you fiddle with gravity until you can explain the various observations. Well, unfortunately, that generates a whole load of problems of its own. In principle, you might be able to get away with the need for dark matter in a galaxy if you apply modified Newtonian dynamics. But it is not risk-free. It generates a whole load of other problems which you then have to go away and think about solving. For every problem that MOND solves, it generates 17 other ones. So it's not necessarily a panacea. It was popular in the early days of missing mass because it seemed like a possibility that MOND was more likely than we're missing some mass in the universe. Now most people think that MOND is not the answer and that we genuinely have a whole load of mass that we need to go away and find. So does it matter? Let's finish with the what are the consequences if we don't have this dark matter, or what difference does it make if we do have this dark matter in the universe? We've said we need it to explain these observations, but who cares how fast galaxies rotate? If they're rotating at the wrong speed, okay, they're rotating at the wrong speed. Does it really matter? Well, there is one major consequence of the existence of dark matter. When people carry out simulations to try and explain how the galaxies are distributed in the universe, how did we go from the Big Bang to the sort of galaxies and stars that we see at the moment, in order to get galaxy distributions that are similar to our observations, we have to have dark matter in the mix. If you try and simulate a Big Bang that generates lots of hydrogen, if you then try and say how does that end up as a whole load of galaxies and stars and planets, then you can't get the answers right. You can't get the universe that we live in within a simulation without including dark matter. Basically, things do not fall together. They don't clump enough to produce galaxies over the length of time that we've had to produce galaxies. We've had 13.8 billion years from the Big Bang to get to where we are now. But that's not long enough to produce what we see unless you add dark matter to the mix. So we think the universe on a big scale looks like that. It looks rather foamy. There seems to be some empty spaces where there's nothing much going on, and there seem to be filaments, and these filaments seem to cross at nodes where we have little clumps. And if we look at the scale, if we zoom into the top left-hand corner, we see that we get a sort of a clump region where we get knots, and those knots turn out to be where the superclusters and clusters of galaxies end up forming. But the only way we can get this structure is by adding in dark matter. Let me just run a little indication of what that structure looks like if you go from the large scale structure of the universe and zoom in to one of these filamentary knots. The scale is indicated by the scale bar. I hope this video works okay over the zoom interface. So we're zooming in, if you'll excuse the pun, into these filaments, and we're seeing where a few filaments join together into this knot. And here we've got a clump where lots of galaxies, huge numbers of galaxies, have been formed into clusters and superclusters. And this effect of how matter clumps together to form these galaxies seems to work quite nicely in simulations that have a substantial element of dark matter. As I said at the start of this talk, if we assume that something of order 84–85% of all the matter in the universe is dark matter, then things clump together the way they should. If we only include the visible matter, the 15 or so percent, the 16%, then we can't get this sort of result. We don't end up with a simulation where the appearance of the universe agrees with what we see from, for instance, the Hubble Deep Field and other surveys of galaxies. We don't get the right structure to the universe. So yes, it matters. So I've said, why is it dark? Because of the interaction between matter and light being different for dark matter. I've given you 3 strands of the evidence, and the 4th strand of evidence is in the handout if you want to read that. And I've said that we think it's either machos or WIMPs, and it doesn't appear to be machos. So at the moment, the only front runner is that it's some particle that we haven't yet found. And if we didn't have dark matter in the universe, we cannot explain how we end up with clusters and galaxies and stars, and therefore we wouldn't be having this discussion about what is dark matter. So yes, quite definitely, it does matter. Thank you for your attention.